there's a couple other little pieces of things we could do here. And one is, what happens when we have two samples? We call that the difference in means. So we sample a bunch of gas stations in Nevada and we sample a bunch of gas stations in California, and we want to compare the two states. Or we sample a bunch of customers at the Mirage and we sample a bunch of customers at the Bellagio, and we want to compare them. We sample a bunch of tourists in Vegas and we sample a bunch of tourists in Reno, and we want to compare them. We sample a bunch of customers at Chipotle and we sample a bunch of customers at Cafe Rio, and we want to compare them. We want to sample length of time to graduation of male or female students, and we do samples of them, or we do samples of female faculty and male faculty and look at their salaries and see if female faculty are paid commensurate with male faculty. There's all sorts of things we can look at where we have two samples. Okay? So in that case, our null hypothesis, H0, becomes the mean of sample 1 is equal to the mean of sample 2. Okay? So, we're going to state in H0 that mu1 equals mu2. The mean of the gas prices in California is equal to the mean of the gas prices in Nevada. Remember that our null hypothesis is always that there's no difference. So the null hypothesis has to be men and women are paid the same. It has to be California and Nevada are the same. It has to be Las Vegas and Reno are the same. It has to be the Bellagio and the Mirage are the same. And then we have a null hypothesis that they're not equal, that mu1 is not equal to mu2. We have to calculate a test statistic and a critical value, just like we always do, and then draw a conclusion. The test statistic and critical value is a little more complexical, though, than it was before. So here's the formula we're going to use to calculate the difference in means. We're going to subtract the two means from each other. That makes sense, right? We're going to take the mean gas price in California minus the mean gas price in Nevada, or vice versa. And then we're going to have a big, giant square root sign. Take the variance, or standard deviation squared, of California divided by the sample size in California, plus the variance, or standard deviation squared, of price in Nevada divided by the number of gas stations in Nevada. Calculate that. And that is going to be our T or Z that we're going to use. Okay? So, our test statistic, actually. A sample of 25 customers in an Indian restaurant spends a mean of $30 with a standard deviation of $10. Sample of 40 customers at a Brazilian restaurant spend a mean of $32 with the standard deviation of $20. Do customers actually spend more at the Brazilian restaurant? Okay, so step number 1 is to figure out how many degrees of freedom we have. And the answer is, we're going to add up the two samples and subtract 2, because now we have two sample means that we're dealing with, so we lose 2 degrees of freedom. So we're going to add up 25 plus 40 minus 2, which means we have 63 degrees of freedom, which is bigger than 30, so we're happy about that part, but it's still not a very big sample. Okay? So, we have a null hypothesis. The mean for Brazilian is equal to the mean for Indian. The alternative is that Brazilian is not equal to Indian, and Indian food is much better than Brazilian food, but that's a side point there. Our test statistic would be 32 minus 30 divided by, and again, this whole thing is under there. That's 10 squared, that's 20 squared, right? 100 divided by 25 plus 400 divided by 40, which is 2 over the square root of 14, and if we calculate that, we get 0.53. That's our test statistic. And again, 63 degrees of freedom. Okay? We already know what critical value to use. It's our old friend, 1.64. And you can go look that up on the table again if you want to. Our test statistic is 0.53. Our critical value is 1.64. Critical value bigger than test statistic. We accept the null. That means that the customers are the same. The people at the Brazilian restaurant are spending the same amount of money as the people at the Indian restaurant. Okay? So, I'm going to give you some actual real-world data. We did a survey of how happy people are working at UNLV, and we have 80 female professors and 100 male professors. And they had an average score. They could rate it as high as 4. So if everybody was really happy, they'd be 4, and if they're not happy, they'd be 0. And they're 2.6 and 2.1, which means that in general, everybody's not very happy. But it would appear from these data that the men are happier than the women. The women are less satisfied with their work and their career at UNLV than the male faculty are. So our null hypothesis would be that the male and female faculty at UNLV are equally happy, and our alternative would be that they're not equally happy. Our test statistic, we take the two means, right? Take the two means, put them in here, subtract them. Take each of our standard deviations, we square the standard deviation. Remember, this is a big, long square root sign. And 80 and the 100. Okay? Do the math, and we get a test statistic of 12. That means we're 12 standard errors apart. That's huge. That's a huge difference. We already know the answer without looking it up. Clearly, women faculty are less happy with their careers at UNLV on average than male faculty are. We have 178 degrees of freedom. That means we're going to use our old friend 1.64. 12.2 is greater than 1.64. Our test statistic is bigger than our critical value. We reject the null. The null is that male and female faculty are equally satisfied with their careers. It means that there appears to be an issue that female faculty are less satisfied with UNLV, less happy working here on average than male faculty are. And again, the faculty as a whole aren't really happy, but the male faculty are happier, more satisfied with UNLV than the female faculty. Okay.